through this book, we'll learn, how to use Hugging Face transformers. But one of the problem with using transformers, is that it is not always possible to train models on your computer, like your normal computer you have. You need what is called GPU. So you need GPU to train models. So what I'll be doing, as I said, introduction to transformers. All the session that we'll do will be some chapters from this book. So today we'll just see chapter 1, which introduce the transformer. The next chapter I will do is allow you to train model, classification tasks such as name entity recognition, such as sentiment classification, any task that is, so the next session will be with that. But if you don't have GPU, this available GPU, so each chapter you can see, you can open in a Colab or Kaggle or Gradient, or then you can run the model, everything. So these are all free resources that you can use to run the model. So for example, now, if you want to use gradient, so if we look at this, you can see this is a gradient. This is a notebook. So if you just click here, chapter 1 gradient, you open it. So you can see this is all the chapters. You can see that chapter 1 in gradient. So this tool, allows you to train models using, GPU, and without having the, need to pay. But they have some caveat, like it's not totally free if you want to use some stuff. But also, if you want, you can open on Colab. So this is a Colab. This is the same GPU, but you can also open in Kaggle. So the main idea, what I'm trying to say, is that today, as I made mention, because some of us don't know about Hugging Face and transformers, then I decided to give a little intro. So today we will see what I would just discuss is more or less about chapter 1 of this book, with many things are added. Then the next subsequent session, we'll talk about how you can use zero shot, few shot and other stuff. But it's good you can have access to this, and I share this in channel so that you can, follow along. So that's the motivation, but also for some of us that, they are doing research in NLP and they don't really have, GPU, they don't have Colab, and you are doing research. We at House NLP will provide, Colab, because this one, if you want to use, for example, this one, all of them, they provide like free, which is like some few hours, but for training deep learning, sometimes it requires like 7, 6, 8 hours, which you need to subscribe to pay. This stuff, they cannot provide you with that. So if you are doing some research related to NLP and you need, subscription, we from House NLP can provide you with, subscribe, Colab, for example. Now we do subscription for people that are using AfriSanti, and we give them, they are using that. So we, if you are doing any research, talk to us, we can provide support for you. So that's about the introduction. And now let's go to, start going. So what is transformers? Now, everybody in NLP and deep learning, we are talking about transformers, but what are they? Why are they giving us state of the art? But before transformers, we have some history in NLP. In NLP, before transformer, this is what we were using: bag of words, TF, word to bag, RNN, CNN. All these are, you can see in this year 1954, all these days. This is where we use bag of word. A bag of word allow us, to turn, a text into, some kind of dictionaries of word, and, and TF-IDF solved the problem where, all related word, given high frequency. So it's just like a TF bag of word with some other stuff, that is TF-IDF. But also we move from TF-IDF to TF models to word to bag, embeddings and stuff like that. And we move also to, neural network architectures to train models such as RNN in NLP. Because here you didn't see a CNN. CNN was mainly before used in, computer vision, but also CNN is also used in NLP. You can see here RNN, different, version of RNN. We have LSTM, bidirectional encoder decoder RNN, different kind of RNN. These are the kind of, in 2014, these are kind of, language, neural network architecture that gives state-of-the-art performance in deep learning. But what breaks this and shatter all this record is the emergence of what is called transformer. So now in 2017, transformer came. What happened is, people from, Google released a paper called transformer. This transformer, so even RNN, you can see before it was started, LSTM bidirectional, and now RNN at the 2014, we have what is called encoder decoder RNN, meaning there is something called encoder decoder. RNN is using something called encoder decoder at this year. But transformer came, and transformer also, though it is using encoder decoder, we'll see what is the meaning of encoder decoder. Don't bother about that. We'll see that in a bit. But what we are saying here is that transformer came with different architecture. And now, since the beginning of transformer, then everything changed. Everything that you will do in deep learning now is based on this architecture transformer. So you can see like, BART, GPT, transformer, Robata, Albata, Distilbart, Reformer, BART. For example, this BART is, from Facebook, BART is also, I think, from Facebook, right? GPT from OpenAI, so you can see Robata, Albata, you can see all these we have also T5, right? So all these are transformer-based methods. So in a summary, the olden days of doing NLP, it started from bug of word, TF-IDEA, word-to-vec. Then it moves to more neural network. So because this one, they are not neural network. If you want to do, for example, scikit-learn, traditional, then you need to use like bug of word, TF-IDEA, or word-to-vec to do this. But when we move to doing neural network, then architectures like RNN and CNN started to come. But with the coming of transformer, which is, what breaks everything in NLP, and also now in deep learning, is this paper transformer. And everything that you see, this one here, everything now is based on this architecture called transformer. Now, what the hell is this transformer that is now changing everything to become in NLP? So let's move on. So what happened? This paper transformer emanates from a paper called Attention is All You Need. Attention is all you need. That's what that paper transformer introduced. And now what is the meaning of this? So you can see this started from people from Google Brain, they published this paper. Now what they introduced is, we propose a new simple network architecture, the transformer, based solely on attention mechanism, dispensing with recurrent and convolution. So this paper transformer that it comes with what is called attention mechanism. Therefore, there is no idea of what is called recurrent RNN. There's no idea of what is called convolution. Before we use RNN, we use convolution, everything. But now this transformer paper, now it comes and, it comes with a single idea that, change the space of NLP, which is called attention mechanism. This is the thing, attention mechanism. That is what changed the whole space of NLP. Everything that you can see now in NLP that give better performance is based on transformers that are based on attention mechanism. From this paper, attention is all you need. And this paper started in 2017. So you can see like the time is not that long, right? Because you can see it now here in 1954, you can see the changes now, like, the graphic, the development is not there, but here recently this one. So now that's, we show that the transformer generalized well to other tasks. So what they did is that they show the transformer generalized well to other tasks. What this means that transformer is not only, useful for one task. For example, let me say machine translation, sentiment analysis, or, for everything generalized for many tasks. And this transformer is based on what is called encoder decoder. So this is the idea, encoder decoder. There is something called encoder, meaning this encoder, this is why you input your text through encoder, and now it output this thing to encoder, and decoder produce what is called output. We'll just see, this is just to show you what is the meaning of encoder decoder, but we'll not go into the detail of this, but we'll discuss in some other session. So you can see here the encoder decoder here. It has, what is called attention mechanism. Can you see that? Multi attention. So this is just because previous RNN, they also have encoder and decoder. For example, as I said, encoder, decoder, RNN. So you can see this previous, architecture, they have what is called encoder and decoder. But what makes changes in this is what we call attention mechanism. Now, the thing is, everything now in NLP becomes using transformers. Everyone that you say in NLP is using, everything is transformer. From Google, from Facebook, if they want to train a new model, it's based on transformer. So now people are saying to transformer, are they the end of history of NLP? Because what is happening is that since the emergence of transformers, anybody that wants to do research, he is not creating new architecture. What they are doing now, people, they are, they will create a model based on this transformer, or they will create, a data set, or they will, do what is called pre-train. So people are now just using transformers. So transformers are good architecture. And now, in fact, there are many studies that concentrate on what is called batology, which is basically studying how, these kind of architectures, transformer, from, BART is one of them, how they started and how they solved. So this is just like telling you what these language models are. All these are also called, don't forget, language models. They are called language model. For example, BART, GPT, CTD, they are called language model. What does that mean by language model? They try to understand language. They try to predict language. For example, if I said, I love this cat, I love this car is, then language model will try to predict the next word. Maybe it can say it's beautiful. So this is language modeling, trying to understand, to work with language. That is called language modeling. So all these things you see, but, GPT, they are called language models. So, so that's it. So, for example, the one BAT is also, so you can see, people don't know the fascinating thing about these language models is that people don't even know like how this thing works. They don't know like how this understand the language. So you can see like now the transformer-based model have pushed state of the art in many areas, but our understanding of what behind their sector is still limited. Just like normal brain, we know normal brain in medicine, people, they don't even know like functionality, how brain typically works. So the same thing in NLP, this neural network, architectures transformer, they don't know. So, people started studying them to find what is really happening. Now, so that's about that. Now there are many other, language models that about that. So one of them here is GitHub Copilot. So GitHub Copilot is also a language model that tries to, predict tests. Predict not tests, code based on what you write. So for example, and the GitHub Copilot was built on what is called Codex. Codex is language model. Let me just try it. So for example, here you can see, I can say, calculate, the number of maybe the area of triangle angle in Python. So you can see this is, I'm not typing this, but this is just giving me, so you can see I'm not the one typing this, but it's just the one, coming. Okay, what did it, okay, perimeter. Okay, you can see, I think it calculated the, so you can see the area of triangle. So you can see here, I'm just communicating with something and it just giving me this. This is called language model. And what is behind this is what is called
GitHub Copilot, which is based on what is called Codex, is language model. So I can say, for example, find find sentiment of a text using scikit-learn. You can see it start loading everything from, stuff like that online. So this is something that allows you to predict. This is what we call, language model. Now we also have another new language model called DALL-E. So DALL-E is a language model recently that if you give it a text, it will generate an image. So you can see this is text, it will generate an image. A store in front of this, it generates an image. A text, the exact same card on top of a sketch of the bottom, you can see an image and it gives us like a sketch, right? So I'm just giving us the general introduction of these models. We'll soon start looking at, just to give, allow you to be on top of what we are doing now. But the problem is that all these language models like DALL-E, GitHub, for example, GitHub Copilot is not a paid one. It's not a free, it's paid one. All these language model, the problem for you, they are not free. You need to pay. So for example, we students from university, we cannot access some open AI language models. You need to pay. There is recent collaboration that allow, that leads to, publication of one of the largest language model called Bloom, 176 billion parameters open access multilingual language model, which is, from, collaboration of over 1,000 researchers, over 70 countries. And this language model now is free, for free to, use it and do everything. You can see Bloom is from Hugging Face. You can see Idris is part of it. I'm also part of this work. And this work is over, like, the authors of this paper there are like over 300 people that, the authors of this paper. So this is a free language model. People can try it and see. Yeah. So, yeah. Okay. Any question before we move on? Any question before we move on?
Yeah, Assalamu alaikum.
Yes.
Doctor, good morning.
Morning.
Yeah. Can this language model be used for computer vision?
Everything, yes. So now, we have these language models for CV. So for example, now, CV, Hugging Face, computer vision. So we have vision transformers. Those are what I saw, text transformers. So we have vision transformers. So you can see vision transformers, but transformers started from the beginning from text. So we have what is called vision transformers. These are them, yeah. So of course there are vision transformers. So yeah, that answer your question.
Yes, sir. Thank you.
Right. Okay. So let's move on. So now we have seen the introduction on transformers and what they are, what are they? And now let's start looking at, understanding, why these transformers. So as I already made mention, there are two advances that makes these transformers known breakthrough. The emergence of the first paper, which is called Transformers from Google Brain, and the emergence of what is called another paper called ULM-FIT, by Savasya Ruda and Jeremy Howard. So these two papers, as we discussed, these two works, they are what brings, more recent work on NLP. So you can see here, as I gave a general one here, you can see we have transformers, but whatsoever. So here we have some kind of a brief, outline. You can see 2017, that is transformer paper. then there is a paper in 2018, ULM feed, then GPT comes, then BART, GPT-2. This GPT is from OpenAI. So when they create more new model with more data set, they created it, they added. So this is GPT-1, GPT-2, GPT-3. We have another model, Robata, SLMR, Debata, GPT-T. You can see all these, there are many models. So as I showed now, for example, now Bloom is a new model that was just released last week. Now, let me just show you how these, models work in some of the NLP tags using Hugging Face Transformer. So you can see here, I give a simple text, right? Dear Amazon, last week I ordered an Optimus Prime figure from your online store in Germany. Unfortunately, when I opened the package, I discovered to my horror that I had been sent an action figure of this instead. As a long-life enemy of the deception, I hope you can understand my dilemma. To resolve the issue, I demand an exchange of Megatron from the Optimus Days. I enclose a copies of my record concerning this party. I expect to hear from this. So you can see this is just a text, and I want to go through this, text to show us some kind of, NLP task. Now, the first one is sentiment analysis. So given this, who can tell us now? We know that this is a text, and we know what will be the opinion on this text. This because somebody is complaining. Now we can use sentiment analysis with this, and it can give us the level. So you can see here we import transformer, from transformer import pipeline. We have create an object using pipeline, classify transformer classification, and now we gonna use this classifier to classify the text. This is the test, right? This is the test. So we classify the text. You can see classify test. And now the output here, we print it as pandas data frame. So you can see it telling us this is negative. You can see the score is 0.90185. So it's telling us this is really negative, right? Now, that is so simple to do sentiment analysis, right? But also question answering. Now, we have this text, right? Now we can ask some question. So how do we do question and answer with this? So you can see here, question and answering. The pipeline here I imported is called test classification. Now here, the pipeline I imported here is called question answering. I create a pipeline called reader. And now this is a question. I give a question. And now, I will give the pipeline, which is the reader here. Question, this is I input the question. Context is the text. This is the text. So you need to give a context, the text, and also the question. So this is a question. This is the text. This is a question. Now I want to, ask question. What does the customer want? So you can see this is it. What did the customer want here? So here you can see, baby order Optimum Prime figure from online. So in this, unfortunately, when I open it, the package, I discovered my order. So this is the summary of this text. This is what we call text summarization. You can see in few lines of code, 3 lines of code, you summarize this text using Hugging Face Transformer. Oh, okay, I'm talking about summarization. No, I'm talking about, what does the customer want? Question and answer, sorry. After reading this, we know the customer, what he wants is just an exchange, right? So you can see the customer, an exchange of Megatron. Just train a model, give a model just like, give a model just text. And now you can see for you, even if you are asked this, you need to go and read the document. But the model now you can see, give answer, we access our model, and now it gives us an answer. This is what we call question answer. But also we can do text summarization. So you can see here, the pipeline, we imported the pipeline is text summarization. And now, we want to summarize the text. Here we summarize the text. You can see all this, then we summarize it, right? This is the summary. Now, recently we have what is called diffusion models. Diffusion models, these are models that try to, given a text, they give an image using transformers. So here is something that I said, I download, instead diffusion, I give a prompt, a photo of Nigerian President Amadu Bari, and now this is the image. You can see it give me this. Can you see that? So a photo, for example, I can say something like this, a photo of, black man on a rock. or swimming. So let's look what will happen. So you can see like it gives us, an image of somebody. Here I put like a photo of black man on a horse. So it give me something like it. Here I put like a cat dancing on a table. You can see it. So these are all transformers. They are using some crazy thing that people think, is this really true? How do nobody give this, nobody give this image, as you can see, it's not an image stored in the model. It's using this text to create this. It's not like something in the memory. No, just recreation. It's recreating something. And this is all about transformers. And the aim, what we want to do is try to understand how these transformers works and how we can, create and train our model. Any question up to now? Any question or discussion, or somebody want to add something? Okay, so right. So the next thing we're gonna say is why transformers work so well. Meaning like why these transformers, they are working well in the sense that we can see like here they are giving us something very good performance, but where they work well. So for you to understand why transformers work so well, we need to understand three things. Number one, something called encoder-decoder framework. Another thing called attention mechanisms. Another thing called transfer learning. So for you to understand why transformer works well, one needs to understand these three things. Attention mechanism, transfer learning, and the encoder-decoder framework. One need to understand them. So now let's look and understand the bit of them, and move on. So the first one is encoder-decoder framework. So what is the meaning of encoder-decoder framework? So this is it. We have a framework. This is called encoder, and this is decoder. So what is their task? So the encoder is responsible for reading the input sequence and producing representation of it. So this encoder is responsible for receiving input of text that you want to do, whether sentiment, it receive the text and produce the representation of that text. So if this text is something, I love a cat, I will input it, and now it will output the representation of that I love a cat. That is the encoder. The coder then read this representation and then reproduce the output sequence. Now the coder will read in this and produce the output. That is it. So encoder and decoder are made of the stack of identical layers. So you can see each encoder and decoder, they are made of an identical stack of layers. So what I mean here is that you can see here we have the encoder, we have multi-head attention, I have some layer here, and then you have feed forward network. So here we can see like here I have one single attention, here I have a multi-head at two, this one and another one, then feed forward. What it's saying here is that each encoder or decoder, it has what you call attention and feed forward. That is it. The encoder and decoder are made of stack of layers. Each layer is made of two sub layers. Can you see that? Each layer is made of two sub layers, a multi-head self-attention mechanism and feed forward. So you can see a multi-head self-attention and feed forward. And here we have multi-head self-attention and feed forward. But here we have two multi-head. But the bottom line is that each layer will have multi-head and feed forward. That is the encoder-decoder architecture. Now, so having understand what is encoder-decoder architecture, now let's move on to understand some little bit more about that. Now, the road transformer, but transformers, we said one of the things is we need to understand encoder-decoder framework. But already RNN also support encoder-decoder. RNN, if you remember here, we talk about RNN, we have encoder-decoder RNN. But what makes them different from transformer, that RNN was not working so well, that now transformers are working so well? So this is what we want to see. So that's why I say this road to transformers, RNNs were the first to use encoder-decoder framework instead of the ad model based on LSTM. So RNN were the first to use encoder-decoder. But the problem here is that, as we can see here, this is what is happening, RNN. So this is RNN, the state, previous RNN. If you have a text here, you input it into RNN and it output a state, right? Have an input, but we have what is called recurrent, meaning, all the input, they are feed forward. So for example, if I want to translate something like this, I want to do translation using RNN. Maybe I have a text called I hate the cat, but I love the dog. But I start, anyway, let me just give it a previous example. So what it's meaning is that here, if we want to do translation in RNN, because they were used for translation, I will feed in this word, the first token here, I put it into RNN, and the second one put it into RNN, the third one put it in RNN. But the problem is, you remember, like, for you to understand the whole complete sentence, you must relate what is the beginning and what is an end. So the problem with RNN encoder-decoder is that they forget some stuff. So when they, as I showed here, like, this is the first input. The first output is now fed into the second output, and the second output is now fed into the third input, meaning like all the input, they have relationship, meaning that they have the contents in the whole complete sentence. Yeah, I don't know if this is understandable, but yeah, so that's the RNN. They have, as I said, encoder-decoder, and this is an example of RNN. So you can see, let me just read something here, maybe it can make more sense. So you can see prior to the current and LSM are the state of the art. Prior to that, these architectures contain a feedback loop in the network that allow information propagate from one to another, making them ideal for modeling. Yeah, so you can see this one that we have here going back, we put it more like in more than input, because here we have input T, like any input that comes, it gives an output state. Can you see that? But the output state is now fed to the next one. So here, this is the second stage. So this is the whole of this one is equal to this. Now, what I was given an example is that when you are translating, you need to know all the contents from the beginning to the end. That is why you can see, like, when they translate this, for example, I give this and translate it, the output is now fed into the next one, so that the next stage will know what is the behind. The next stage will know what is behind. This is what we human beings, because when somebody just talk to you, even if you hear the last word, but you didn't hear the first word, you ask somebody, what did you say? But you heard some part of the last word. So it meaning that for you to make sense for the text, for any text, you need to understand it all in all. So that's what they are saying. RNN receives some input, feed it through the network, and output a vector called hidden state. You can see this is the hidden state. At that time, the model feeds some information back to itself through feedback loop, which make it use in the next step. So you can see, like, it feed it this here. But the thing is, this can be more clearly, as we can see here. One area where I added, as I give an example, is translation. Yeah, so, but this is it, the representation of encoder-decoder of RNN. So here we have input. For example, I want to translate a text called transformer are great. This is a text, transformer are great. Now what I want to do is to give, this is encoder and this will be decoder. Now what this means is that I will start imputing this one, my first word, transformer, the second one are, the third are great, this one. Now the state will now be outputted into the second encoder, and now this. So you can see that the structure of encoder-decoder in RNN. But the problem with RNN is this. One weakness of this actor is that the final hidden state of the encoder creates an information bottleneck. What we mean here is that there is what is called vanishing gradient.
So as I was giving an example, so here you can see transformers are great. Now, the last input, which is this, will now be the first input into the decoder. So in the encoder, the first input is transformer, second is A, third is grid, and this is the last input. Now, what will be the input of decoder? The last input here, this is the last input. But the problem here is that since we are giving this, the last input to come here, and the next one will come, it may make the RNN to forget what it learned the state here, because it given the last one, as I was giving an example, like, you know, when somebody is talking to you, you didn't hear the first word and you hear some last part, you ask him to, you know, repeat it. That is, you didn't hear. So that's also for RNN, because you are putting, if you are putting a long sentence, you know, long sentence, then because you are feeding to the decoder the last part, then it means that the first part, the state in the first part, the may not be, you know, that is what we call information bottleneck. It will forget. You know, so because RNN, it has to represent the meaning of the whole input sequence, because this is all the decoder has access to when generating output, because the decoder has access to only one state. That is the problem of RNN. So what is the solution? The solution is what we call attention mechanism. That is the solution of RNN. So the solution is called attention mechanism. In attention mechanism, what is happening is that, you know, instead for the transformer, for the architecture to have only, because in RNN, they output a single hidden state, only one hidden state. You can see that, only one. So the idea is to have attention mechanism. So the idea, attention mechanism, allowing the decoder to have access to all the encoder's hidden state, not just the last one. So you can see here, now we can have the decoder to have access to all the hidden state. So the hidden state for transformer, for this one, this one, this one, you can see this is it. That is, you know, the solution that attention transformer brings. As well, we saw that RNN support encoder, decoder, but they give only a one hidden state. And now there is maybe some issue of, you know, vanishing gradient, forgetting to catastrophic forgetting and stuff like that, which make them not suitable for other. The solution is to use attention mechanism. You know, we can see attention is a key component in many modern neural networks. Understanding how attention works was developed for RNN and will put us good in shape. So attention here, it works in also RNN. Yes, RNN has a single state, but we say, okay, can we have attention? So attention was also available in RNN. We can see this is RNN, meaning that what is attention doing? Let's give just like a brief. So attention, the idea behind attention, instead of producing a single hidden state, we can see a single hidden state. Instead for the input, the encoder output a hidden state at each step that the decoder can access. So we can see that each hidden state here. But however, using all the state at the same time will create a huge input for decoder, and so some mechanism is needed to prioritize which state to use. But you can see here we have many states, every state, the decoder has access to it. So there is no issue of forgetting, right? Because the problem here, issue of forgetting. Now the decoder has now access to this state. But the problem is, decoder has many states to try to think which one should output. Given all these state from transformer, R, grade, the decoder has access to all these state that if we are doing translation, what this translate here, what translate here, what translate here, decoder has access to this one. But now the problem is we have many states. Which one should decoder focus on? Which one should decoder focus on among all these four states? That what brings us to what is called a self-attention mechanism. So we can see here attention in RNN, a 4 months attention. Although we can use attention with RNN, there will still be a major shortcoming. Using RNN model for the encoder, the computers are inherently sequential and cannot be also parallel. So the idea here is that, you know, you can see here attention mechanism here also in RNN, they have, you know, problem to assess which one. The solution, as I said, is what we call self-attention. Self-attention, what is it? The idea of the self-attention comes in a key transformer architecture. So the idea of self-attention, and also another problem is that in RNN attention, this hidden state, you cannot parallelize the task, meaning you need to do each one individually. which is a very huge problem. You cannot do, parallelization of any other stuff. So this is where self-attention comes in. A new modeling paradigm was introduced to dispense the recurrent altogether, and instead of relying entirely on what is called self-attention. So we can see that in transformer, we can do parallelization. Like you can have, attention on encoder, you can have attention on decoder. Unlike attention mechanism in RNN, you only have, attention on decoder. You cannot have attention on encoder because you cannot do parallelization, because RNN is having such kind of recurrent. You cannot do that. So one of the problem that transformer solve is like the transformers, they are what we call self-attention. So given in encoder and decoder, you have, you have self-attention in that, and now you can do parallelization. So this is one of, the breakthrough in transformers. Any question before we move on?
Assalamu alaikum, doctor.
Yawa.
All these texts, are they going to be converted into vector space before all this process going to take place?
Yes. So that's that's the encoder decoder. So this one you can see, this is encoder, this is decoder. Now what you are imputing to your text, you are, before even to go into encoder, it should be embedding, right? Which is some kind of form of vector space. You can see that. It goes into this. So yeah, so this is your encoder. It should be that. Yeah, so vector space, you remember here as we talk, all these classical NLP, like bag of word, TF-IDF, some stuff like this are using like just representing our word in some stuff. But since we started using word to beg, embeddings and RN classical, this one we feeding our network with some kind of vector to our model. And yeah, that is it. All started even into transformer and every other thing. Yeah, does that answer your question?
Yes,
and
doctor.
also, yeah, and also
okay, go ahead.
I'll also
go
hear
ahead,
that. Yes, and also here that you see, like we give an example, like give something. It's not like we are doing this text, giving it at the back, at the backbone. This text is now taken and now feed into the architecture. The text needs to be converted first into some kind of vector space, and now it's not like the model is understanding this text. The model, it must be converted into some format. Yeah. Okay, go ahead with the question again.
Okay, doctor. Thank you. Apart from this attention and self-attention, is there any possible other kind of attention in training the model?
I don't understand what you mean. So attention is, we will talk about this in detail, but here I just given, a very layman's, stuff. So all this attention and stuff is when you are training the model, it's using this attention. Your attention mechanism and everything is part of the architecture. So when you are training a model, it basically using the attention mechanism, encoder, decoder. So yeah. Does that answer your question?
Yes, thank you.
Okay, so to recap, what we have been saying now is that we show that transformers are now the state of NLP. They break anything. We are no longer using this method. We are using transformers, and now we have seen the only thing that transformer brings is using what is called self-attention in encoder decoder, because RNN already they have encoder detector architecture, but what break this kind of stuff is that transformer models now they are using what is called self-attention, and we have seen a lot of other stuff about that, and we talk about we just go through trying to see, let's understand what these transformers are doing. We said one of the things is encoder decoder. We said this is encoder, this is decoder. And another thing is attention mechanisms. And now this is, we started looking at, attention encoder decoder in RNN. And this is it.
we saw that one of the issues to solve those forgetting issues in RNN is to introduce what is called, attention mechanism, so that there is output in each and every cells, but the decoder can, decide which one will be best. I will share this. You can read it. This is just a bit of intro, so you can read more about this. But we also said that even though the RNN architecture support what is called attention, it still have a problem. The problem here, we said, although we can use attention in RNN, there was still major shortcoming. Using the current model for encoder decoder, the computation are inherently sequential and you cannot be parallelized. So that's the introduction of what we call self-attention transformers. And now with that, now you can see you have self-attention to input and encoder, and you have self-attention at decoder. Yeah. This is just a bit of intro of this. When we are interested in this working, we can discuss more about it in detail. But just now to let you know some kind of terminologies, so that when we come through, you will understand this kind of terminologies that, when you train a model, somebody, you can say, you put in something in encoder and decoder and so, but learning the technicality of these, we can do them some other time. Yeah, so now we have understand this step, which we talk about, why transformer works well, the encoder decoder, we understand attention mechanism. Then the last one is called transfer learning. Now, let's look at this one, the last one. So a final piece was meeting to get transformer revolution started. The final phase is what is called transfer learning. This is the final phase to get transformer, a revolution. We now understand transformer can work so well. The thing is, the original transformer paper, what happened is that it was trained on very large text, and the text, it was trained is to do what we call language masking prediction, to predict the next word. But now, since transformers say they works well, how can we use transformer, for example, for sentiment analysis, for question answering, for whatsoever? And not only that, how can I use transformer? If I train a transformer in English, how can I adapt this transformer to maybe train on Hausa or on French? That is the missing part. And now what solves this is what we call transfer learning. What is the meaning of transfer learning in a nutshell? Is that the idea of transfer learning is this. Let's assume, I study a course called, medicine, and I understand a lot of stuff in medicine. So, and now I move into, to specialize in something like maybe physiotherapy. I think physiotherapy is not medicine, right? Something like that. So some knowledge you have in medicine will really be helpful, to make you do well also in physiotherapy or something like that. So in NLP, what we mean by transfer learning is this, like this. If you train, for example, a model in English, you can now do learning you can use that model you are trained in English to train model in Hausa. So that's the missing piece. So here you can see in the original transformer paper, the translation was made from scratch on a large corpus. However, in many practical applications, we don't have such kind of large corpus. So since transformer was trained on large corpus, that is why it is so good. Now, what about if you want to train a model that is maybe in different domain, maybe in legal domain? Does that mean you need to create large corpus in legal domain again to create another model? No, you can do what is called transfer learning. So what is the idea of transfer learning? So in classical supervised learning, what we do is this. When you want to train a model, you have domain A, maybe, you want to train a model in domain A, meaning domain maybe in medicine. And now you train that model, and now you can do prediction in domain A. Or you have a data set in domain B, you train your model on data set of model B, which is maybe legal domain, and you do prediction in legal domain prediction. But what makes, transfer learning different is this. I have a large data set on domain, in medicine, large data set in medicine. Now I train the model with that data set, right? Body A, you can see it, right? Body A, right? So here we can see we have what is called head A. You can see here
in classical supervised learning, we have only the model. We have model only. We train the model and we do prediction. But in transfer learning, the model is divided into two. We have what is called the body. We have what is called head. Now, we have a body and head. Now, the thing in transfer learning, when we train this model, now in maybe legal domain, and now I want to train a model in maybe, if let's assume this is legal domain, and now I want to train a model in medicine, in medical domain. What I need to do is, I don't need to train a model from scratch. I will use the body, what that model learned in legal domain, because it learns some weight and other stuff. I will leave it. What I will need to do is just to change the last part of the model, which is called the head. How can I change it? I will now train the last part with my medical domain data, so that the model now will, utilize or, take advantage of everything that is learned from medical, from legal domain. So also here you can see we have domain B, we have, body A. You can see that. What we mean here is, we have head B, right? And we have prediction in B. So here we have domain B, but here you can see we can use body A, and now we can use head of B and make prediction in B. So this is the whole idea of transfer learning, meaning that you can train a model on separate domain and now change, whether you freeze some layers or to do some stuff, and now, change the last layer to make prediction. So this last piece is what makes, NLP transformer, becomes, break the state of the art in NLP. So yeah, because this transfer learning issue is more common in computer vision, but now it is now used in NLP. Okay. Yeah, so I want also to discuss also some kind of stuff that we made mention. So this kind of transfer learning, this is the work from people, many people, for example, those that bring this idea. Did I mention something here about that? Okay, anyway, this kind of transfer learning is a work that breaks through this kind of take the transformer step, to the next level. It's the work from Jeremy Howard using a paper called ULM Pit by Jeremy Howard and Sebastian Ruda. That is the thing that breaks combination of transformer and the combination of transfer learning. That's now what makes transformer being used in every task today. So there are some tasks we want to understand before now. There is what is called pre-training. There is what we call, domain adaptation. There is what is called fine-tuning. So what is pre-training? Now, as I said here, you can have, a data set in maybe news domain. I train this, I train it from scratch. Training from scratch here is what we call pre-training. So maybe you have billion of text. Now, when you train it here, this is what we call pre-training. That is when you train from domain data. It's called pre-training. Now, what about if I want to do, sentiment analysis and on maybe data set in Hausa? So because this data is trained on English with billion of data, now I want to change this, fine tune this last head to do sentiment classification in Hausa. This kind of thing is what we call fine-tuning. Can you see that? So if you look at it, pre-training is a process of training a model on a large or level text. So here, large or level text. Yeah, this is a ULM Pit paper. Yeah, okay, this is what I was saying. This is ULM Pit paper. So this language model, train a language model on large or level text. For example, you just get a text from Wikipedia, very large, then you train a model. Training this model is what we call pre-training. The data set you need to train this model is not level. For example, now when we are doing sentiment analysis, remember, we need to level a data positive. No, a language model is just giving the model very huge amount of data and let the model to understand, some structure. The model will understand what is synonym. The model, if you train a model on large language model, the model will be able to understand that good and bad are opposite. Excellent, good, they are the something, synonym. Because you give the model
very huge amount of data. The model on itself will try to figure out all this linguistic structure. That is what we call pre-training. We have another thing, what is called domain adaptation. What is domain adaptation? So domain adaptation is this. Now I train a very huge model on a data set on Wikipedia data. Now I want to, change the model maybe to, different domain, maybe to movie review domain. Now, so I will take this language model and now do fine tune it, something like that, to the data of domain I'm working on. That is what we call domain adaptation. If you look at domain adaptation, it's the process of adapting a model trained on a domain to a new domain. So I train a model on Wikipedia data, very large data set, but I want to do like sentiment analysis, because in sentiment analysis, I know that, we will be talking about movies. We'll be talking about new movies, but that movie data is not available in this Wikimedia data. So you need to fine tune this model to adapt it so that it will understand some concept about movie data. That is what we call domain adaptation. The goal of domain adaptation is to learn a representation of the data that is useful for the new domain. Can you see that? But the goal of pre-training is to learn representation of the data that is useful for the downstream stack, everything. And the last one is what we call fine-tuning. So what is fine-tuning? So now I have a large language model, this one, large language model. Now I want to do sentiment classification. Now fine-tuning is you need to provide this model with some level data that is labeled as positive, negative, neutral, that the model will be able to classify. Because the model now here, as you can see, the model now knows some data about movie. The model knows many movies, some stuff like that. Now what you need to do is just to give this model, to fine-tune this model with data set in movie that you label as positive, and negative, so that the model will be able to classify what is positive. That is what we call fine-tuning. You can see is a project of adapting a model trained on a large level data to a new task. So you can fine-tune it for sentiment classification. You can fine-tune it for question answering. You can fine-tune it for text generation. You can find, this is what we call, so fine-tuning means, adapting a model to a particular task. That is what we mean by, fine-tuning. So the era having transfer learning and having also the, transformer, the combination of these two, transfer learning and transformer, because transformer allows you to train a model from large amount of text, and transfer learning allow you to adapt to new model. The combination of these two now break the history that everything now becomes using transformer. So you can see here, as I discussed, transformers are the end of history of natural language processing, meaning, everything now is using transformer. Also, we can see from here, everything now here from transformer, any model you see from 2017, anything that gives state-of-the-art performance is based on transformer model. You can see that GPT, everything now is based on transformer-based model. So now, having a look at this, we can see here we have GPT. So GPT-2, is decoder only model. BAT model is encoder only model. So you remember we discussed about the transformer, they are based on encoder and decoder. But some models, language model can be only encoder and decoder. For example, GPT is a decoder only model, but it encoder only model. So look at how the representation. For example, here I have encoder and have decoder, and now I want to translate some text. So this, so look at what is happening. So this is the input, and now the embedding is now transformed into the embedding, the vectors embedded. Now this embedding with some signals are added and now fed into encoders, right? And now there is some kind of magic that is being done, using attention mechanism, which we may not discuss here. But what is happening, you can see at each step, the output here, you can see, the decoder is giving, this output, a student, which is basically the translation of this. So this is just to show you what encoder decoder works. But we will discuss this kind of, details about this in subsequent session, but just to let you know what is happening, encoder and decoder that's doing. Here is translation task. Not only that, you can see we have many kind of, model GPT-3. So these all language models, they started, with adding data. So for example, you can see here the GPT-2 started, this is a very small number of parameters. They add parameters, number parameters. So GPT-3 is 175 billion parameters. 175 billion. So GPT-3, I think today, this is a language model that is the best language model, I think, on earth. We can say that it, is close to human understanding. It can do crazy things, stuff like that. So this is, GPT-3 with some 175 billion parameter. But now we have what is called Bloom, that as gave an example, which is the language model now, which is now Bloom, 176 billion parameters. So this is the largest language model on earth now, free 176 billion parameter. Even GPT-3 is 175 billion parameters. Even though the Bloom performance now is not on the par with GPT-3, GPT-3 is better than Bloom from the paper if you read it. But I mean, the good thing with Bloom is that it's free, open access multilingual model, as I said, with over 100 researchers covering 70 countries. So that is it. There is something called continual pre-training. So I introduced something previously. So here you can see, like when we train a model here on a data set, we fine tune it to our another thing and to give us a new domain. But there is what is called continual pre-training. What is a continual pre-training? So pre-training process is iterative. So let's assume that I train a model on Wikipedia data, and I have like maybe 1 gig or 2 gig data. I train it, and I have 2 gig, but I want to adapt that model to clinical model. Then you can continue pre-training, not adapting, not fine-tuning. So you can see here, as I give an example here, you can do fine-tuning. We can fine-tune the head, to make prediction, but we are still using the body of language A, for example. Body of, okay, this example. For example, we are still using, if we have body of A, a language model I train, and now the head, I just change the head to fine-tune to make prediction on a new domain. But the idea is, instead of me to do fine-tuning, because this model has already been trained, why can't I continue training this model on my new data, not fine-tune it? To continue training this model on my new data, because it already learned something on this domain. So let me continue training on this data. This is what we call pre-continual training. So this is what we call continual pre-training. So here I have a data. Now I have new domain here. You can see protein domain. Now this is pre-trained BAT model. Now I continue training pre-trained BAT on from the pre-trained BAT checkpoint to do that. And now finally I can fine tune. This is what we call continual pre-training. You can see here we have different kind of BAT. So for example, here SciBAT. So it may be trained on, was trained from scratch. So you can see pre-training now is 2 types. You can see pre-training from scratch, and you can see training continual pre-training. So for example, here we can see like a clinical BAT, Wiki for books, they continue training from BAT using clinical data, Bluebird, PubMed BAT, So so if you are talking about training a language model, there are 2 types, from scratch and continual pre-training. From scratch is just to train a language model from scratch, and continual pre-training is just to adapt to the new domain. If you have new domain data, to continue training it. And continual pre-training gives from literature a very good performance. Okay, that is that about that. And let me a tour of transformer application that we discussed. So here, this is a given text. If we want to do test classification, we can see here, like, we train, we import pipeline, and we specify the pipeline to be test classification. And now we can see here, we do sentiment analysis, right? We can do name entity recognition. Now we can take, a pipeline. We can say which, again, it's non-name entity recognition and aggregation strategy simple. And now we can create an object called NAT tag. And now here we can have, given this text we have, then we can see that it gives us Amazon. What is that? Organization. Germany is location. everything. You can see this is named entity recognition. We can do question answering, given, a question, and given the calling the pipeline, question and answering. We can see that, we can, this is a prompt, a question, given a question, and it gives us an answer. We can do text summarization, given a text, we want to summarize it, calling the pipeline, the summarizer. You can see summarizer, and we do summarizer. We can do translation. You can see here, I give, translator. We can see the pipeline. We give the translator model here. We can see, we give the text translator, the text we want to, when we create the object translator from the pipeline, we always use the pipeline. So from the translator here, we put the text. We want to clean up the text space through minimal length is 100. Now we translate here from what, with our English to, I think it's French. But you can see this one, German. You can see this is pre-trained language model from English to DE, Germany. You can see it do translation. We can also do text generation. What is text generation? Text generation is that given a prompt, you generate text related to that. So for example, here you can see the pipeline we use is called text generation. The rest one, dear Bambele, I'm sorry to hear your order was mixed up. You can see this is a, response. So for example, here you want to generate something. You can see, you can combine this text, which is this. We already have the text. This one, you can see the text. Yeah, we can see the text. We have customer service and the rest one. So we can see here, because this is a response, so we can see here this, it generates this automatically. I'm sorry to hear that we are mixed up. You can see the model generate everything here. Can you see the order was completely mislabeled, which is very common. Can you see that this is just the model that from this one, you just give it a response, just a prompt that the model will be able to complete everything. And now you need to give it the context. Can you see here? This is what I gave, the text, which is this, you can use the generator here. We create generator. And what is a prompt? The prompt is given the context and now the response. So you can see it generated. Now that is what transformer is, the general introduction of transformer, but still we have not used, we have not seen how can you fine tune transformer to do that. That's what we're gonna, do in our next session, but still I think I need to finish with this, some stuff. So all this what we are seeing using this pipeline, they are from what is called Hugging Face transformer. So what is Hugging Face? Now there is, so yeah, just a pointer. Well, is that all we train if you wanted to do sentiment analysis, question answering? Is it all it needed? No. So what is happening? We might be wondering why where is the training taking place? Now the problem is that all of the model we have used are publicly available and already fine-tuned for the task. Remember, I told you if you want to do language model, you need to do fine-tuning, meaning you need to take already language model train, and now you fine-tune it to a particular task so that you can do sentiment analysis, question answering, whatsoever. So this thing that I'm using is already fine-tuned for, text summarization, is already fine-tuned for question answering, is already fine-tuned for name entity recognition, is already fine-tuned for, all of these tasks. So now if you are doing something for your own data, you need to fine-tune. Do you understand what I mean? So in general, however, you want to fine-tune model on your own data. So if you are given data to do sentiment analysis, you are not coming to take this fine-tune model test classification to give you. You are not going to use this one. You are not going to use this one. You need to fine-tune your data. For example, the AfriCenti we gave. Now you need to take that data for AfriCenti to fine-tune your model. When you fine-tune your model, then on your data, because these data they have been trained on, have been fine-tuned maybe on different data. For example, the translation we saw is fine-tuned on English to DE. So you cannot just take this one and translate for Hausa because it hasn't been fine-tuned for Hausa. So you need to fine-tune your model on Hausa data set. That is what we're going to see in the subsequent session. But before that, let's quickly look at what makes easier for us to do fine-tuning, to do transformer. So there is a whole new ecosystem called Hugging Face. Now, there is a problem because people have been creating these transformer models, and now when they create this transformer model from different kind of organization, it becomes difficult to monitor these models and now to have a unique API. Now the Hugging Face comes to create this kind of stuff. They have different kind of libraries, Hugging Face transformers that allows you to use different kind of model. We have the Hugging Face. People upload their model because we can see BART, Robata, and everything. And this Hugging Face transformer, they can be used for text, they can be used for image, they can be used for any other thing. Then we have also Hugging Face tokenizer, which is also a library. Remember, tokenizer, it given a text, it changes that text to some kind of tokens. So Hugging Face tokenizer is a library that allows you to divide a text into tokens. Which we have a Hugging Face dataset. So what is Hugging Face dataset? So Hugging Face dataset, it's a library that allows you to load, upload your dataset, do data versioning, commit, everything related. So let me show us this. Yep. So if we go here, we can see that we have Hugging Face dataset. You can see many dataset in Hugging Face that you can use. So you don't need to look for dataset. Now there are many datasets. Our also AfriSanti dataset will be uploaded here. I will upload our AfriSanti dataset today so that people will just load their dataset from Hugging Face. So you don't need to. And you can see here there are different kind of models. If I click here in Hugging Face models, you can see model for sentiment class. You need to select the task. For example, let me say test classification, computer vision. Okay, natural test classification. So for example, text classification, you can see different models, you can see them, but you can also, so you can see we have different kind of model, fine tune for Roberta sentiment. Let me see this. So you can see this is, model trend for sentiment classification. I can put something like this. I hate this car, and we can see it will give us whether what is this. Level 0, okay, level 0, level 1, level 2. So level 0 I think is negative. So here, okay, but let me change to another model, maybe the one that will give us something that's negative. Japanese sentiment, no, generic. Okay, let me search for sentiment. Oh, let me use Niger Senti. Yes, Niger Senti. So Niger Senti, I can say wannan mutumin wannan mugu ne, na tsane shi. So let's look at it, because Niger Senti was on Hausa, was fine-tuned on Hausa, so it will be able to tell us this is a negative sentiment. Anyway, before you finish loading, as I said, you can upload your model. So that's our model for Niger Senti uploaded. You can also, Hugging Face has tokenizer, and you can upload your dataset. Dataset provide many other things, like uploading dataset and calculating metrics, like Hugging Face, like cited line metrics. There is another library called Accelerate in Hugging Face that allows you to run models on multiple GPU. There is a new library in Hugging Face called Evaluate. So this library Evaluate allows you to evaluate your models using just like scikit-learn. We have metrics in scikit-learn. So this Evaluate is just like scikit-learn metric that allow you to evaluate find performance of your model on different. Then lastly, we have Diffuser, which is a new library that allows you to generate giving a test, something like this, a photo of Africa, a photo of African girl. Let's see, something like this. So when I have this, this is called Diffuser, which is given a text. Diffuser library is like given a text. What it basically does is, given a text, it gives you, an image. Then finally, the main challenges with transformers is that, language, NLP tags is dominated by English language, everything is in language, and data availability. Data is very scarce. You cannot get data every time, and which is basically the, difficult part of, a phone of I say a phone of Africa. Oh God, a photo of African girl. So these are some of the challenges with transformers. Another one is opacity, meaning that we still don't know why this model. My connection has gone. So I don't know whether the model has gone. Anyway, my connection disconnected, so it cannot give me. So yeah, opacity and bias. So there are many kind of bias. Maybe maybe let me introduce it. Maybe let's see what will happen now here that we said, a girl, African girl. Let's look at the picture it will give us. So there is kind of bias in our, models, meaning these models now, they are not so good in, data that's not been trained. So if, for example, now, if you say African girl, you may see that it gives you something, different, or bamboo or something like that, just like, those issues. So these are some of the challenges of that. So as I said, okay, let me go back to that thing. Yes, look at it now. Wannan mugu ne, na tsane shi. Can you see it give us as negative, which is 100% negative. Kun gane 100% negative. So model then can be able to translate this, that this is negative 100%, which is also 100% negative. So you see, like fine tuning. So here means we fine tune. We took some language models, Robata, and we fine tune it to our data set for Hausa. So this is what I was saying. What we did basically was, we take a language model called Robata that has been trained, we take its body and fine tune it with our Hausa data set. We fine tune it. And now with Hausa data set, you can see now we can do prediction given a data set. So that's what is called fine tuning. Any question? Lastly, now this today, what we do basically, we introduce, the tasks, what is transformers, how they work, and we'll be able to see, how we will be able to fine tune a model, so that we will be able to do that for our AfriSanti. Given any data, how can we do fine tune the model? How can we use zero shot classification? How can we use few shot classification? So this is something that we'll see in the subsequent section. But today, what we did, we basically introduced what is transformers and, why are they, and their a brief history. And now, as I said, now, these transformers now, in NLP, what is happening is that everything that comes is not changing the architecture of transformer. Everything, they are based on transformer, but recent thing in NLP is just creating data set, doing fine tuning, doing whatsoever. Everything relies now on transformers. Okay. Let's look at the last example I was given. This one. I need to log in anyway. Okay, let me tell this guy. Okay. All right, so let me turn this. So we can see here, I'm using the diffusion model, which I imported here, diffusion, and I'm asking the model just to, look at it, it's still the phone, a photo of African girl. Let's see something as well. So here I say a photo of African girl. Okay, no, there is a mistake. Look at the model, what the model give us, you know, a photo of African girl. So what I would say is a photo of European girl. Okay, so let's look at the photo of European. You can see photo of European girl. So this, you know, models diffusion, this library, diffusers, what is doing is giving a text, it just converts to, you know, let's see photo by a photo of President Muhammad Buhari on a chair.
So, photo of Sharholia.
I will some with Sharholia, I have modeling. Sharholia.
Kalmar ai bata dade da fitowa ba.
To model din ba zai san Sharholia ba. Bari mu ga. Ai kuma ma President Muhammad Buhari on a horse zai saka shi mako akan horse din saboda bai taba jin
ai bai ma iya ta hawa bane.
Bari mu ga me zai ce.
Phone fa ka saka ba photo ba.
Ban san me yake fitowa ba abin. Gala abin da yasa.
Ina ce ga Baharin nan.
Okay, you know, anyway, so that's you know, what the summary of our today's discussion. We now understand that, you know, transformers are the state-of-the-art NLP techniques. We are no longer using, if you want to get a state-of-the-art performance, we are no longer using this kind of, you know, old approaches, what bag of what, idea, what to be, RNN, LSTM, CNN. What we are using is we are using transformers. So we can see from this year, transformers now, all of this one, they are based on transformer-based model, bar GPTT. So what we are doing now, people, what are doing is just like creating whether, you know, domain-specific transformer-based model, you know, or, you know, fine-tuning the model. That is what people are currently a lot of doing. But there is no, since 2017, there is no architecture that is, you know, something that is transformative, such as transformer. Everything that we build, that is built now, is based on transformer. Yep. So anyone with question or anyone want to add something? And I think tomorrow also we can continue. So to make a very recap, we understand that our team here are participating in